In this video, we're going to kind of finish up chapter 9. We're going to talk a little bit more about double replacement reactions, but now we want to focus on a different type of double replacement reaction. And this is one where you form molecules as your product. Okay, so this is a complete review of double replacement reactions that we've seen in the last video and in previous videos. I want to draw your attention to this part here where it's talking about the products. Remember, in a double replacement reaction, two new compounds are formed, which may be a solid, water, an acid, or an aqueous ionic compound. So we've talked about solids before. We've seen aqueous ionic compounds before. In this video, we want to focus on water and acid formation as products. And we've seen that already in a previous video where we formed water, but now we want to just kind of in more detail look at that, I should say. All right, so this isn't just a complete repeat. We're going to be talking about a few new things. So like it says here, double replacement reactions can lead to the formation of a weak acid or water instead of a solid. And so when that happens, when a weak acid has formed, remember that it doesn't completely ionize. So what do I mean by that? Well, for strong acids, make something a strong acid is that it completely ionizes in solution. Whereas for weak acids, okay, they don't completely ionize. They stay together as molecules. So even though they're aqueous, they don't completely break apart in solution. All right, so that might be something that's a little bit tricky, something we talked about before, but we need to recognize then when I have an aqueous weak acid in my equation and I want to write the net ionic equation, I can't break that apart. So I need to be able to identify weak acids. And how do you do that, you might be asking? Well, remember there's 7 strong acids. So if you have an acid that's not one of those 7 strong acids, it's a weak acid, just by definition. So if none of that made sense, let's just do an example problem together, okay? So write the net ionic equation for the reaction of solutions of hydrobromic acid, which is a strong acid, and sodium benzoate, and it gives us the formula for that ion here, okay? So let's begin by writing the conventional equation, as always, okay? So we have hydrobromic acid plus sodium okay, this is also aqueous, gives us, okay, so remember this is a double replacement reaction, so A, X, B, Y, A, Y, B, X, okay, that's what we're going to get here. So we are going to have H with Y, and remember now this is a compound, this H here, let me actually do this. Let me change this color here so I can explain something. Okay, that hydrogen, okay, is the proton that came from the strong acid. And because the benzoate ion took that proton, all right, it's now going to be an acid, okay? So we're going to consider this an acid, and it's going to be aqueous, okay? So that's why I highlighted that proton. So when you're doing these reactions, basically, whoever gets that proton on the product side, whoever gets that hydrogen in these acid reactions here, becomes the acid in terms of this benzoate, okay? So it might not be technically right, but it's probably the best way for you to think about it and to understand what I'm about to say next, okay? So maybe it is technically right, I don't know. So this is going to be sodium bromide, okay? This is also aqueous if you look on the solubility charts. Okay, so now we're going to write the total ionic equation. Everything that's aqueous is going to break apart almost. So we'll talk about that in a second. So we get a proton plus the bromide ion plus this plus C7H5O2. Now, I said almost. This guy is the weak acid. That's what I was saying. How to identify the weak acid. He's the guy that got the proton from the strong acid, hydrobromic acid. So what's going to happen here is because he's a weak acid, this compound is actually going to stay together. Okay, so this compound is going to stay together because weak acids, even though they're aqueous, do not completely ionize. Okay, so he stays together. This is going to be sodium plus bromide. Okay, so now that's what I was talking about the proton too, so you could tell. So these guys are gone. And what I'm left with is a proton H plus this guy here gives me this. So this is the net ionic equation. Okay, and this is a weak acid. Okay, so he stays together. All right, let's do one more. All right, write the conventional total ionic and net ionic equation for each of the following pairs of reactants. Okay, so I think there's two examples that are coming up here. So let's do that. So I'll just do this one with you and then we'll go forward. So the conventional here, so these guys are aqueous. This guy's aqueous. Okay. What you're going to get, and we've seen one like this before, again, it is double replacement. So we're going to get water, or HOH as I'm writing it. Okay. Write the guy from here and the guys from here, plus lithium sulfate. Okay. And remember, because they're aqueous, we didn't bring this 2 over. That would be wrong. Okay. That comes from when we have to make the compound balance in its charges. Instead, because it's aqueous, we look on our ion chart and we see the charge of hydrogen, +1, a proton, and we see the charge of hydroxide ion, which is a -1. So I need 1 proton and 1 hydroxide ion. And then what I'm going to do instead is when I balance the equation, okay, then I can put a 2 in front of here and a 2 in front of here, okay, to balance out the lithium. So now when you look at it, right, I have 2 hydrogens there, 2 hydrogens there, 1 sulfate here, 1 sulfate here, 2 lithiums here, 2 lithiums here, 2 hydroxides here, 2 hydroxides here, okay? So that's why I wrote it as HOH instead of H2O. It's just to help you visualize what's going on here. But if you wrote it as H2O, it would still be correct, okay? So this is going to be a liquid, okay, water, and this is going to be aqueous. Okay, and again, we've done problems like this before. So now when you break this apart into its ions, okay, for the total ionic equation, you're going to have a proton, okay, hydrogen, aqueous, we have 2 of them, right, plus the sulfate anion, plus 2 lithium ions, lithium ion batteries. Maybe you're using one of those right now. Maybe it's dying. Hope not. Hydroxide plus H. Oh, excuse me. Not a plus. Sorry. Gives me HOH to those liquid. Plus, I'm going to run out of room. 2 lithiums. These guys are aqueous, okay? SO4, 2 minus plus, okay? AQ. Kind of run out of room there. Okay. So what's going to cancel here? Well, by the look of it, the sulfate ion going to cancel. The lithium is going to cancel. And I'm left with 2 protons plus 2 hydroxides gives me 2 waters. Now, one thing that I should say here is that because all of this, you see these coefficients, how they all have, they're all the same, they're all 2. Okay, what you actually want to do here is simplify it, right? Because this net ionic equation should have the simplest coefficients possible. So you might want to simplify it to give yourself this, okay? Okay, so simplified. So this is the net ionic equation, okay, for this reaction. Okay, let's do one more problem, then I'll stop the video, and then I think there'll be one more video actually after this. All right, so write the conventional total ionic, yep, we get it, of this. So why don't you pause the video and do this on your own. Okay, so here we go. So these guys are going to be aqueous and aqueous. Okay, and what we're going to get is potassium bromide, aqueous, plus HNO2 aqueous. And this is a case, you see that proton came from the strong acid, hydrobromic acid. It's going over here now. And if you actually are familiar with naming acids, or you remember, that is nitrous acid, and that is a weak acid, okay? Because it's not one of the 7 strong acids. So now when we do our total ionic equation, write this out, potassium plus NO2 minus plus proton plus Br minus bromide ion gives me potassium ion plus bromide plus proton. Whoops, no. See, I'm making a mistake now. It's getting late. So I'm going to change the color here. This guy stays together because he's a weak acid. What am I doing? I'm breaking the rule this whole video is dedicated to, okay? So weak. Okay. So weak acids stay together. So now if I go here, all right, potassium, potassium, bromide, and bromide, and I'm left with, okay, NO2 plus proton gives me this weak acid. Okay, so that is my net ionic equation. All right, so that's it for this video, I believe, and then we're going to go on to talk about double replacement reactions with unstable products in the final video for this chapter. So I'll see you there.